Hello students. So in this video, let us focus on the periodic properties. So we already completed all the classifications including modern periodic table. So what is left in this chapter is periodic properties or periodic trends. What does it mean by these periodic trends? For example, atomic size, ionization energy, electron affinity, electronegativity, metallic, non-metallic properties all comes under these periodic properties. Like for example students, you already know these elements exhibit, they have their own atomic size, yes or no? But all these elements are clearly systematically classified based on their atomic numbers and according to the configurations. So definitely we need to observe the trend, yes or no? Trend means how the atomic size is, what is happening to the atomic size from left to right in periods and top to bottom in groups. Why? Because atomic size is one of the main factor behind the reactivities, also behind many properties, melting and boiling, physical properties as well as chemical properties also. So that's why not only atomic size, like ionization energy, what is electron affinity, what is electronegativity during the bonding, how do they behave, how do they attract, how do they repel, everything, all these factors, and what is the flow happening in the periodic table left to right, top to bottom, that is called as periodic trends. So first of all, to start the discussion, atomic size. So atomic size or atomic radius. So how to define this atomic size, students? The distance from the nucleus to the valency shell is called as atomic size. That's it. Radius of an atom, yes or no? The distance from nucleus to the valency shell is called as an atomic size. Like how can we calculate the atomic size? Like for a single independent atom, is it possible to count the atomic size or atomic radius? The answer is no. Why? Because students, to measure we have one parameter called as nucleus, yes or no? We have one reference here. From the nucleus we can calculate what is the end, what is the other end. Do we have any other end, other reference, other parameter there? No. Why? Because that is electron cloud. Can we expect a strict electron there? No, electrons are not stationary, they are moving and it's a cloud, yes or no? So single independent atoms we cannot calculate the atomic sizes. But how to calculate? Every time we have to calculate the atomic sizes when these atoms are in bonded situation, at least when they are very close to each other. So that if two atoms comes close to each other, we can calculate the distance between two nucleus, yes or no? And half will be the atomic radius. Got the clarity? The distance between the two atoms nucleus, half will be the atomic size of each and every atom. So that's how we can calculate the atomic size. Students, it is different as in terms of atomic radius. Atomic radius is different as the distance between the nucleus and the valence shell. Atomic radius is expressed in mainly angstrom unit or picometers. You have to remember this, the conversions: 1 angstrom equal to 10 to the power of minus 10 meters and 1 picometer equal to 10 to the power of minus 12 meters. So let us check the trends as well as the types of atomic radius. Atomic radius, students, mainly expressed in three ways, three types. One is called as crystal radius, second one is called as covalent radius, third one is called as van der Waals radius. So first crystal, covalent, van der Waals. What does it mean? We all know that these atoms, student, these atoms, they do not exist independently, clear. But do they exist like all in the same flow, in the same way? No. Some are metals are there, some are ionic compounds are there, yes or no? Some are covalent compounds, and some are they do not bond only, like noble gases, right? So based on the type of atom we are finding atomic size, we have a particular type of the atomic size. Here it is called as crystal radius or also called as metallic radius. So obviously metallic radius means for which type of atoms are we calculating the atomic size? For metals, right? Iron, we have iron bench, iron scale, yes or no? It is made up of atoms, right? How to calculate that? It is all surrounded by different atoms, yes or no? Different iron atoms, only iron atoms only, or gold. Gold contains gold atoms, right? How to calculate? The distance between the nucleus between two gold atoms and half will be the atomic radius of that gold atom or iron atom or any other metal. Sir, why it is different from metals to other? That I will explain. First, this is called as crystal radius in terms of metals. So half the internuclear distance between the adjacent atoms in a solid metallic crystal is called as crystal radius or atomic radius or crystal radius or metallic radius. So right students, metals they do not bond, but there is a separate category of attraction called as metallic bonding. So they develop these attractions. So but in that phase only we can able to find the distance between two metal atoms, and half the distance will be the crystal radius. Not only for iron or gold, for in general for any metals. Look at here, the example is given as sodium. Distance between two sodium atoms is how much? 3.72 angstrom unit, students. What is the crystal radius? By 2, that's it. So how much it is? 1.86 angstrom units is taken as the atomic size of each sodium atom. So this atomic size in terms of metals is called as crystal radius. You have to remember that. Covalent radius. What is covalent radius? The bond forms by sharing the electrons is called as covalent bond. Yes or no? What is covalent bond? The bond forms by sharing electrons is called as covalent bond. Sharing electrons means, students, definitely they are in bonded situation. Their atomic orbitals overlap. That means the atoms are very close to each other. Yes or no, students? If they are very close to each other, the distance is increasing or decreasing comparatively. Once think, if they are very close, the distance is decreasing, no, not increasing. Yes or no? They are very close to each other. Why? Because they are completely in a bonded situation. So same definition, the half the internuclear distance between two atoms which are held together by a covalent bond. There in terms of crystal radius, adjacent atoms, yes sir, they are not bonded, but here they are bonded together. That means they are very close to each other. And here for example, you look at two homonuclear diatomic molecule, heteronuclear diatomic molecule, which means if both are same atoms, hydrogen gas H and H, hydrochloric acid HCl, that what indicates, but the definition is same. So it is called as half the distance between two covalently bonded atoms is called as covalent radius. Students, homonuclear and heteronuclear, H2 HCl, that's the example. Next, here some examples are given. In Cl2, Cl bond Cl, the bond distance, the internuclear distance is 1.98 angstrom units. So the covalent radius of chlorine is how much? Divided by 2, which is 0.99 angstrom units. In diamond, carbon bond carbon, the distance is 1.54, hence the covalent radius is how much? Of each atom, 0.77 angstrom units. So as the number of covalent bonds between the two atoms increases, covalent radius decreases. This point is very important, students. So what the point says? If number of bonds between two atoms increase, for example, C single bond C, C double bond C, C triple bond C, number of bonds are increasing or not? If the number of bonds are increasing, what is happening to the covalent radius? Is decreasing. Why? Why? Because, students, if more are the bonds, the atoms will come more and more closer. Why? Because the extent of overlapping will be more. So that's why, so now answer, where there is a more covalent radius, for single bond or for triple bond? For single bond. Triple bond, there are 3 bonds, so atoms are more closer to each other. Yes, sir, students. So obviously what will happen? The covalent radius will be decreased. You have to remember this point. Why it is happening? If more are the number of bonds, overlappings of the atomic orbitals will be more, so that atoms comes more and more closer is expected in the case of triple bond. So right, next. So we have covalent radius completed. Next, van der Waals radius. Van der Waals radius, students, crystal radius is mainly for metals in metallic bonding. Covalent radius only for covalent bonding. Yes or no? Van der Waals radius is for the atoms which do not bond between the non-bonded atoms. Example, helium. How to calculate helium atomic size, students? Helium doesn't show its attraction, doesn't have any bond, right? Helium is a normal monoatomic molecule. It is only one atom. Yes or no? It is a noble gas, obviously. So how to find the atomic size? You know how to find? We have to maintain all the helium atoms under high pressure conditions. We have to make them closer to each other. Under low temperatures and high pressures, what should happen, students? What we have to do? We have to make 2 helium atoms, not only 2, many are there. We have to make ultimately all the helium atoms come closer. If these 2 atoms come closer, then we can find the distance between 2 nuclei or not. Half will be the helium. We can find the distance between 2 helium atoms, yes or no? Are they by their own they are coming together? No, we are making them to come together, yes or no, by maintaining high pressure conditions. So this radius in terms of non-bonded atoms is called as van der Waals radius. Van der Waals, it is a scientist name, mainly given this name for these weak attractions which they develop between atoms and atoms when they come closer. So this bonding is called as van der Waals radius. This attraction is called as van der Waals attractions, and the radius is called as van der Waals radius. And look at here, students, which radius is more? Is it crystal radius or covalent radius or van der Waals radius? Answer, you just think. So first of all, radius means what? Distance, right? Yes or no? Where the atoms are not bonding, definitely the distance is more. In which case the atoms are not bonding? In the case of van der Waals radius or not. So that is its bond distance is more. not in the sense like the distance between two atoms is more. In that same similarly atomic radius is also will be more. Next, crystal radius. In crystal radius also metals also do not bond with each other, but they have attractions. Okay, we are not making we are not making iron atoms to come closer. So by their own, because of attractions, they are already adjacent to each other. So next position is crystal radius have more atomic radius than the covalent radius. The least radius is expected in the case of covalent. Why? Because already the atoms are in bonded situation. They already closer to each other. So that's why van der Waals radius is more than crystal radius, which is more than covalent radius. Next, variation of atomic size in groups, periods and exceptions. Groups, top to bottom. What happens to the atomic size, students? Top to bottom. Top to bottom, every time a new shell is getting added. Now for example, let us take the first group elements. Hydrogen 1s1, next lithium 2s1, next sodium 3s1, next potassium 4s1. Every time what is happening? A new shell is getting added or not? That means the distance from the nucleus to the valence shell increasing or decreasing? Increases. In groups top to bottom, atomic size increases, atomic radius increases. Got the clarity? Next, in periods. What happens in periods, students? Let us take any period, second period elements. What are the second period elements? Beryllium, boron, carbon, nitrogen, oxygen, fluorine. Yes or no? In these elements, so is the new shell is entering in the valence shell? The new shell is not entering to the valence shell, right, students? So the atomic size, does it remain same? Atomic size doesn't remain same. In periods from left to right, atomic size decreases. You know why atomic size decreases in periods? The new shell is not getting added, but what is happening is effective nuclear charge is increasing from left to right. Lithium, how many electrons? 3 electrons, 3 protons, right? Next, beryllium, how many protons? 4 protons, 4 electrons. Boron, 5 protons, 5 electrons. Carbon, 6 protons. So every time what is increasing? Protons are increasing, right? Along with protons, electrons are also increasing. But here the point is, are all these electrons situated in a single point to show the negative nature? No. But what about protons? They all behave at, they are all located at a single point. So now which power will be more? Of course, by number both are same, protons and electrons. But while showing the power, which is more? Positive power, nuclear charge power, or electron power? Nuclear charge only. Why? They are all located in a single point. Electrons like a cloud. That's why. So left to right, what is happening? Effective nuclear charge is increasing. That means positive charge is more and getting more and more. And the electrons, are they entering into the new shell? No, electrons are entering into the same shell. So if more is the positive power, electrons are negative charge, what happens, students? Slowly the electron clouds comes closer, 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 closer to the nucleus. Yes or no? So that's why left to right, atomic size decreases. Why? Effective nuclear charge is more. Sir, why not in groups also different protons are there? Na? Why in groups also effective nuclear charge is more, students? Correct. But there is an effect called as shielding effect is more in groups. That means inner electrons can shield the nuclear power so that the valence electron it doesn't get that much of nuclear attraction. So that's the reason why in groups top to bottom atomic size increases, in left to right in periods it decreases. Exceptions, if it decreases in left to right, students, in periods, which elements are least atomic size? Obviously noble gases. Yes or no? They are the last elements in the period wise. So but in the noble gases, due to the interelectronic repulsion, the size is larger than the corresponding halogens. That means, students, halogens being chemically unreactive, they do not show this attraction. They have effective nuclear charge is more, but their lack of electronegative character is the reason why the valence electrons undergo repulsions between them, and somewhat the size of these noble gases are more than the expected. Got the clarity? That's why they comes under an exception. Next, comparison of sizes of anion or cation with the parent atom. Parent atom means sodium, sodium ion, chlorine, chloride ion. Which is more in size? Let us take sodium. Students, let us take sodium. Sodium atomic number is 11. Yes or no? It contains how many protons? 11 protons. How many electrons? 11 electrons. And let us take sodium ion Na plus. And it contains how many protons? 11 protons. But how many electrons? 10 electrons only. Which power is more dominating? Positive power. If positive power is more dominating, the valence electrons comes closer or not? That's why a cation always smaller than its parent atom. Remember students, a cation is always smaller than its parent atom. As well as, let us take one more example with chlorine. Chlorine atom as well as chloride ion, Cl and Cl minus, which is in this case, which is bigger in size, which is smaller in size. In this case, anion, negative charge is bigger in size than its parent atom. Why? Because chlorine atomic number is 17. It contains 17 protons and 17 electrons, right? But chloride ion contains 18 electrons and 17 protons. This time which power is more? Negative charge is more. Yes or no? If negative charge is there, that incoming electron undergo repulsions with already present electrons, right? So that's why the size is increases for anion. Remember the point, the statement. Cation is always smaller than its parent atom. Anion is always bigger than its parent atom. If the charge increases and this power also increases. Got the clarity? So right, next. Ionization energy. What is ionization energy? The minimum amount of energy which are required to remove an electron from the valence shell of an isolated neutral gaseous atom is called as ionization energy to form a cation. An element is there. Let us take sodium. Let us take a sodium element, students. It contains one electron its valence shell. Sir, sodium loses one electron. Loses one electron means, does it loses one electron like in general? No. We have to provide some energy. That energy is called as ionization energy. How much energy you need to provide in order to remove that electron is called as ionization energy. And from a neutral isolated gaseous atom, meaning is we cannot observe this energy when all the sodium atoms are present. Yes or no? Why? Because if you provide that energy will be absorbed by the remaining sodium atoms also. Can we get the precise value? No. You have to isolate one atom, that is isolated. If you are isolating a single atom, that is a gas phase. Yes or no? That is a gas. A single atom is always a gas phase, or you can convert a solid into liquid, liquid into gas. Is ultimately got a single atom, right? That is isolated gaseous atom, neutral. Does it have any charge? No. That's what in this atom, if you provide the energy, this energy is so precise. Whatever the electron, the electron gets ejected out, it takes some energy. That energy is perfect. Yes or no, for a single atom. So the minimum amount of energy required to remove an electron from the valence shell of an isolated neutral gaseous atom is called as ionization energy. So if X lost one electron, that is called as 1 IP. X is a general element. If we can remove the second electron also, that is called as second IP. If we can remove the third electron, third IP. Fourth electron, fourth. Got the clarity? That is the first ionization, second ionization, third ionization. Units of ionization IP. Why it is called as IP? Because ionization energy also called as ionization enthalpy or ionization potential, all are same. So electron volts per atom, kilojoules per mole or kilocalories per mole. So these are the units of IP you have to remember. So next, first, second and third and fourth ionization energies of magnesium and aluminium are respectively given. Look at here students, look at here. First look at magnesium. What is the value? First IP value 737, right? 737. This is the first IP. What's the meaning of first IP? This is the energy which is required to remove the first electron. Look at the second IP, this much energy. Okay, energy is increasing, yes or no, to remove the second electron. Here it is 737, here it is 1450. Now look at the third IP, suddenly it becomes 7000. A biggest jump is expected here, yes or no? A biggest jump. And from here it is normal 10,000 only. There is not a big difference here. Why a biggest jump is expected here? That I will tell you. Look at aluminium. First IP 577, second IP 1816, third IP 2744. But look at the fourth IP 11,000. Where the jump is expected here? Here for the third IP, right students? After third IP for the fourth IP. So the reason is magnesium contains 2 valence electrons. If they lost those 2 electrons, now magnesium ion achieved the noble gas configuration. If it got the noble gas configuration, is it easy to remove that electron which is in the stable state? No. That's why to remove that third electron from the noble gas configuration, it requires high energy. Now when it comes to the aluminium contains 3 valence electrons. If it loses 3 valence electrons, first IP, second IP, third IP, now it achieves the noble gas configuration for the fourth electron. To remove the fourth electron, does it easily lose electron students? No, it requires high energy. Got the clarity? That's why these jumpings are expected. So different elements have different IP values. Next, variation of this ionization potential in periods groups. IP, top to bottom, what is happening students? Atomic size, top to bottom atomic size is increasing, yes or no? So for which atom we can easily remove electron? For example, hydrogen, lithium, sodium, potassium, these are the elements group wise. This is hydrogen, only one shell, lithium, two shell, sodium, 1, 2, 3, 3 shells, potassium, 1, 2, 3, 4. Where electron can be easily removed? Here or here? For hydrogen or for potassium? Answer, electron can be easily removed here in the case of potassium. Why? Because it is far away from the nucleus. It is far away from the nuclear attraction. We can easily remove. Yes or no? So top to bottom ionization energy, the energy which you need to provide is more or less. What is happening from top to bottom is becoming less and lesser. That means ionization energy top to bottom decreases because atomic size is increasing. Now what happens from left to right? Left to right in periods, what happens to the atomic size? The valence electrons are coming closer to the nucleus. So now atomic ionization enthalpy increases or decreases? Ionization energy increases. Why? Because electrons are going closer to the nucleus. More is the nuclear attraction. Effective nuclear charge is more. You need to provide more energy to remove that electron. Yes, students, that's the same. So top to bottom in groups decreases, left to right in periods increases. So helium is the element with the highest ionization energy, right? Got the right, correct. It is a noble gas and it is a very small size. Next, so from their locations in the periodic table, predict the correct order of first ionization energies of fluorine, chlorine, bromine and iodine. So for these elements, which has more ionization energy? You answer students, fluorine. Fluorine belongs to the second period element, followed by chlorine, bromine and iodine. Top to bottom, what happens to the atomic? All belong to the same group. Top to bottom, what happens to the ionization energy? Top to bottom ionization energy decreases. That means which has highest IP value? Fluorine followed by chlorine followed by bromine followed by iodine. This is the order. Got the clarity? So and all are belong to the same group. If it's the different elements, the order will be different. So right. Next, electron affinity. So ionization energy is about energy required to remove electron. Yes, sir, no. Electron affinity is about when electron is added, what happens? What is the energy change which is expected? That is called as electron affinity. Let's read the definition. The amount of energy released when an electron is added to an isolated neutral gaseous atom in its lowest energy state to produce an anion is called as electron affinity. That means this time not removing the electron adding. Why? Because metals can lose electrons easily. What about non-metals? Do they lose electrons? They will gain electrons during the reaction. So this property is mainly defined in terms of non-metal, students. So if X is an element, if it gains one electron, it becomes X minus and this much of energy is released, which is EA in terms of electron affinity. Units of EA are electron volts per atom or kilocalories or kilojoules per mole, same. So fluorine example is given. Fluorine gains one electron according to its valency. If it gains one electron, students, how much of energy is released? Minus 328 kilojoules per mole of energy is released. If energy is released, it is indicated with negative symbol. If energy is absorbed, it is indicated by a positive symbol. So these non-metals, highly reactive non-metals, if they get that one electron, they readily achieve the noble gas configuration. So that's why they release energy. If they have energy, what does it mean? Instability. Releasing energy, more stability, remember. So here, students, in terms of oxygen are given, first EA, second EA, same like ionization potential. Electron affinity values also we have. If one electron is added, first EA, second electron is added, second EA. Sir, no, some elements depends upon the valencies configurations they have. They can gain the respective number of electrons, either 1 electron, 2 electrons, sometimes 3 electrons also, like nitride. So here oxygen is the example. If it gains 1 electron, look at the value, minus 141 kilojoules per mole. What does that minus indicate? It releases that much of energy. So oxygen valency is 2, it will gain 2 electrons, yes or no? If it gain that extra electron, now O minus becomes O minus 2. Look at the EA value, which is how much? Plus 780 kilojoules. That means this time is it releasing energy or absorbing energy? For the second EA, it is absorbing the energy. Why? It should release now. Why? Because already it is a negative charge. Yes or no? Now you want to add this electron to this negative charge. Negative electrons also negative. What happens? They will undergo repulsions. To overcome the repulsions, we need to supply some energy. So that's why first EAs are always exothermic reactions, second EAs are always endothermic reactions. You have to remember where this energy is utilized in order to overcome the repulsions between the negative charge and the incoming electron. Right. So students, next variation of electron affinity. You have to answer this. Top to bottom, atomic size is increasing. Which atom can easily, gain the electrons? Hydrogen or cesium? Like in terms of cesium is a metal, of course, obviously, but in general, in terms of atomic size, answer. Which can easily gain electron? The smaller size atom or bigger size atom? Smaller size atom. Yes or no? Why? Because effective nuclear charge will be more. The incoming electrons is closer to the nucleus. Got the clarity? So electron affinity top to bottom decreases. What happens to the left to right in periods? What is happening? Atomic size in periods decreasing. So electron affinity is increasing. Got the clarity? Why? Because atomic size is decreasing. Electron affinity increases. So next, electron negativity. So we discussed about two factors. One is ionization potential. Second one is electron affinity. Ionization potential is for cations, for losing electrons. Electron affinity in terms of anions, when an atom gains electrons, energy changes. What is electronegativity? Electronegativity is calculated for covalent molecules. That means the atoms which are bonded by sharing the electrons. That means covalent molecules. Yes or no? So what is electronegativity? The tendency of an atom in order to attract the sharing pair of electrons towards itself in a bonded molecule is called as electron negativity. What is electron negativity? Is not gaining or it is not losing. What it is? It is the tendency to attract the electrons. That's it. That is electron negativity. Look at here, two images are given here. One example is between hydrogen. Okay. Both hydrogen gas example, both sharing one electron each. You can see the electron. This is the bonding electron pair. Yes or no? This bonding electron pair, where it is located, is it more closer to the hydrogen side or more closer to this hydrogen side, left hydrogen or right hydrogen? This electron pair is exactly in between. Let us check the other example. One more example. In terms of HCl, there also hydrogen valency is 1, chlorine valency 1. They are also sharing one pair of electron. But look at here, this pair of electrons, the bonding pair is more closer towards hydrogen side or chlorine side. It is more closer towards chlorine side. Why? Because chlorine's electron negativity is more. What is the meaning? It has more tendency to attract the electrons. It is a halogen, 17th group element. If it can gain one electron, it readily achieves noble gas configuration. Here the doubt, sir, why it is not gaining? It doesn't have that much of capacity. Why? Because there is look at the opposite element. It is still hanging that pair of electrons. Sir, no. If instead of hydrogen, if it is a metal, what happens? That metal lost already. Here chlorine will gain. It becomes chloride. But does the capacity difference, is it more? No. That's why chlorine is trying to take that electron and hydrogen is trying to hold that electron. That's why they develop partial negative charges and partial positive charges. So this attraction is called as electronegativity factor, students. So electronegativity will be calculated by taking ionization energy plus electron affinity values divided by 2. So if this difference, if the difference between combining elements, if the electronegative difference is less than 1.7, then that means between combining elements, one element doesn't have that much capacity to lose, other element doesn't have that much capacity to gain. Then what bond we can expect? Covalent bond. If it is less than 1.7, the difference of electronegativity. If it is equal to 1.7, 50% ionic character, 50% covalent character, both are present. If it is more than 1.7, then definitely ionic bond. That means definitely one atom lose, one atom gain. Which atom loses? Less electronegative element loses. Which atom gains? More electronegative element gains, right? Variation of electron negativities in groups and periods. This also same trend. It is also about attraction of electrons. Yes or no? So what is the factor which is here? Effective nuclear charge. Top to bottom, atomic size increases. So which atom can easily gain electrons? Small, like not gaining attraction, but still which can show attraction? Small size atom or big size atom? Small size atom. Yes or no, students? Why? Because effective nuclear charge. Big size atom, the valence electrons, does it get much of nuclear attraction to attract other electrons? No. That's why top to bottom electronegativity decreases, left to right electronegativity increases. Fluorine, chlorine, bromine, iodine, which is more electronegative? Fluorine. Why? Because its valence shell is closer to the nucleus. Iodine is 5s2 5p5, far away from the nucleus. Does it attract much? No. So fluorine is the element with the highest electronegativity. So these are the periodic trends, students. We have also this electronegativity factor is called as nothing but non-metallic nature also, and opposite to this electronegative character is called as electropositive character, which is called as metallic nature, opposite to the electronegative character. So these are the periodic trends, students, which defines all the elements, physical properties as well as chemical properties. So we are done with this chapter. Thank you, students.